Okay, so real pleasure to introduce Yejin Choi, who's our next speaker from University of Washington. She works on NLP and I think is a perfect follow-up to Yintat's talk about sparks. Yejin's also a MacArthur Fellow and is a great speaker, so looking forward to your talk.
Okay, thank you. So yeah, I'm excited to talk about what might be possible and not possible with the sparks of AGI, especially what may be seemingly impossible but possible and vice versa. So along that direction, let's start by imagining a future that may or may not happen. So NeurIPS 2050 may not even happen if we solve everything and there's nothing to do other than going to the beach. But if we were to still have it, what would that be like? Maybe we burnt too many GPU hours and we have to move to metaverse because of the climate change. Nobody travels anymore, or we had to even move to Mars. So the venue is now Mars for the first time in 2050. And in that conference, would you be excited to see more few-shot engineering? What happens with the scaling laws at that time? And what sort of applications would we work on? I really wish, apparently plumbing is one of the hardest challenges for AGI, so we'll see what happens with that. Maybe, AI starts writing papers so much so that there will be best human paper award separate from best paper award, given to, human being the first author of the paper. And maybe there will be panels among ChatGPT and humans. And perhaps in that conference, in fact, ChatGPT writes the paper and also reviews the paper, and you let both of them to speak to each other for rebuttal period on behalf of you. Diffusion generates your slide deck, and then Nerve can present your talk. And then why bother going to any of the talk, because ChatGPT can summarize that talk. So maybe all of this is complete nonsense. If quantum computing does happen, and now we have this QPT with the perplexity near 1, at which point, again, we might just go to the beach. But, it's also possible that we might still be debating whether AGI is around the corner or not, and whether we solved a dock level embodied AI or not, and whether compositionality really is a thing. So, having said all this nonsense, so this talk is going to be first about the possible impossibilities and then vice versa, and then I'll discuss some paradoxes that we can think about. Disclaimer though, I'm gonna end up asking more questions than being able to provide good answers, so please don't expect too much. So for the impossibilities, it seems like AGI might be just around the corner, and everything seems so possible. And in that context, is there anything really impossible? And we feel like scaling might be all you need, and so forth. So on one hand, we feel like we're so close to AGI. But on the other hand, as Intad also alluded in his talk, there are many things that we don't yet understand. And perhaps it's a little bit similar to what happened with the physics. So 1878, there was this student, Max Planck, who considered to major in physics. And the professor, Philip von Joly, recommended not, because in that field at that time, almost everything looked almost already solved. and all that remains is to fill a few unimportant holes. And so then the student said, I don't wish to discover new things. I only want to understand the known fundamentals. And he went ahead and created this entire new field, quantum physics. So since then, there are a lot of things that are weird, almost counterintuitive, at least for people outside physics proper, such as dark matter, Schrödinger's cat that may be both alive and dead simultaneously, and wave-particle duality. These are all conceptually quite strange things to learn about. And I do wonder whether there may be something like that going on in the way that we understand or don't understand intelligence, in the way that we don't understand or understand transformers and so forth. And there may be some interesting counterintuitive things that we can investigate further. And there are many questions one could ask. I could throw questions like, can AGI happen with or without embodiment? Whether RLHF can really fully align LLMs to factuality or not. But I don't have any answers to this. I just touch vaguely on the compositionality in this talk. So this talk is going to be based on this paper on arXiv. It so happens that the first 5 authors, co-authors, are all women. We didn't plan for this, but maybe that was fate. But anyhow, so the question is, does Sparks of AGI, aka GPT-4, or my favorite language models, can do multiplication or not? So we ask, and actually, it kind of looks correct, but it's a little bit incorrect. At least the first digit is correct, and the last digit, usually the first digit, last digits are correct. But I'm told that you have to ask it to think step by step, right? So we do that, and there's a different number now, but it's also slightly incorrect. So if you ask this systematically, what happens is that GPT-4 can do 3-digit by 3-digit multiplication, about 60% good. And depending on how you look at it, this is like mind-blowing good, or it's a little bit worse than you may have expected. What's your guess for 4-by-4-digit multiplication?
Higher than this.
Huh?
I think higher than this. This like this could be more successful.
Oh, how did we do this? So that we can increase the number. I will show you that if you do a scratchpad, more like really. Allowing it to think out loud, the chain of thought reasoning, it does much better. I'll show you the number. But without doing that, just like asking directly, turns out 4% accurate for 4-by-4 and 0% for 5-by-5-digit multiplication. Again, by humans, I cannot do this either, so maybe we can justify that. It's okay. We're asking too much. So I know a lot of you probably think like, why do we even care about multiplication? So in this paper, we actually also look at dynamic programming problems and Einstein puzzle logic problem. But in this talk, I'm going to just focus on multiplication because A, it doesn't require compositional multi-step reasoning. B, it's just easy for us to discuss and think about. And in some sense, I'm just curious, especially seeing how amazing GPT-4 is with language proficiency and being able to compose text in a way much, much better than what I'm capable of. It's just fascinating to understand where the boundaries are. So in that sense, multiplication might be interesting. But that said, never in my life did I imagine that one day I would actually write a paper focusing on multiplication so much. But let alone that some other people like it too. So Kevin Murphy said he liked the paper, despite the fact that it's just about multiplication by and large. So here's another question. But maybe GPT-4 didn't see enough of multiplication examples. So what happens if we do supervised training? So we cannot do GPT-4 scale supervised training because the API is not provided by OpenAI. But GPT-3 Da Vinci model does have API that you can pay for to do supervised training. So we train GPT-3 Da Vinci size with 1.8 million, or 80% of that example. So 1.8 million examples include all these combinations of, let's see, 1 by 1 digit, 2 by 1 digit, 2 by 2 digit, 3 by 1 digit, 3 by 2, up to 4 by 2. And then we randomly split that into 80% training and 10% for dev and test. What's your guess that how well would this do? This is supervised training on really a lot of examples. Let's just see, like a show of hands. How many of you think this seems like transformers should be able to do? There's a lot of examples. I mean, should be able to do in the sense, how good though?
So the test is 4 by 4 again.
Test might include any of these numbers, like 4 by 1 or 4 by 2. 4 by 1 is probably trivial. So it's like it's a in distribution test case right now. So we actually didn't know like what to think of, or at least I felt like on one hand I can believe that this must be doable. On the other hand, I don't know. But anyway, so it's actually not very easy to train this, even to do well on the in-domain cases. Of course, out of a domain case, it gets even worse. So, but then, we thought, oh, maybe this is because of tokenization issue, because it may not know the number boundaries correctly. So what if we train GPT-2 from scratch? So we cannot do, by the way, academics don't have enough GPUs to train GPT-3 scale model from scratch, but we can do GPT-2 XL. So let's just say, don't worry about English words or any words. Only worry about tokens that are numbers. So we only have 10 tokens. Then what would happen? Do you think this is trainable or not? Just number multiplication. So I wasn't sure what to expect personally. Maybe some of you like shake your hands and this should be impossible. So it turns out it's very hard to train GPT to XL, only using 10 tokens. It's only like 10% accurate. So there's something interesting about how pre-trained language models that have seen language does seem to perform better, despite the fact that tokenization may have not been optimal for them. Yes?
So in all these examples, are you trying to get the answer immediately after the prompt?
For the time being, yes. Later, I will show you the other case as well. Because like as we all know, chain of thought is important. So anyway, the tokenization in itself may not be the issue. So, okay, you wanted to see this, a scratchpad. So we tried many different scratchpad, the best we could. And it turns out with the scratchpad, the GPT-4 does do so much better. So on 3 by 3 digit, it's 92% good. It's not perfect yet, but it's getting so much better for sure. So, but now the question is, does that generalize to a slightly longer digit? And it turns out not really. Accuracy decreases down to 4% on the longer digit. I mean, you can imagine that this should do worse, but not like that bad. It's not, I don't think these results are all that obvious to guess. So then, if you're a skeptic, then you have to do supervised training on that. But actually, before showing you that, I wanted to share a bit of this community reaction to these empirical results, because we do see messages like, transformers absolutely can learn through multi-step algorithms in context and generalize to arbitrary problem sizes. What's going on? And here's one such example that shows how to teach algorithmic reasoning using in-context prompt engineering. So we opened the paper, and it turns out their results are similar to ours in some sense, in that from here they go to here for subtraction. For multiplication, they appear to have a bigger jump. So first of all, it's not 100%. You're not going to be very impressed if I tell you I can do multiplication 80% good. But moreover, this multiplication, there's a fine line. So they also found that GPT-4 is not very good if you go beyond the 3 digit. So what they do is they dissect longer digit down to 3 by 3 or less, and then sum them up. So it's not quite the same as actually being able to do 4x4 in one go. So there's some dissection that's required. But I mean, maybe that's all, correct way of doing it in the end. But for the purpose of understanding what is possible and not possible, we found, at least I was puzzled or surprised even, that the numbers are lower than what I would have anticipated, considering how amazing it is with language-based generalization. So then we decided, okay, maybe we should do supervised training with the Scratchpad on GPT-3, and just curious, what happens if we do that. So, but it's very expensive. If you want to do 5x5 2-digit, this is, we don't have that kind of money. I can barely spend maybe that much. So I'm cheap. So that's why we tried out of curiosity. And it does really work much better, as you may have expected. It's like 96% accuracy on in distribution, but then it doesn't generalize very well on out of domain. I mean, meaning here, longer digit multiplication.
What do you mean by Scratchpad?
Oh, Scratchpad is similar to the chain of thought, but more elaborate version, where, this kind of stuff, showing exactly how to do step-by-step reasoning as a few shot examples that we provide. And the thing is, this example can become a bit too long for longer digit. So
just to clarify, in this slide, the in-context example is the same as the query, but with one number off by one. Was that always the case, or is this just something that's in the slide? You see what I mean?
What did I
like the example that you're so the example you're providing in context is 999 by 866, and then you're asking for 9.
Oh no, this is not. This is just by chance. We do it randomly.
Okay.
Right. So where was I? So why does this happen is curious. Anyhow, so we were, after archiving this paper, we also wondered about grokking. What about grokking? First of all, who knows what happens if you keep paying OpenAI more money? But to the extent we were willing to pay, we didn't see that happening yet. And again, this is like a really interesting question, at least for me, that how do we know whether grokking was going to happen but didn't happen versus it's not going to happen at all? And if so, why? Like, why multiplication is fundamentally harder than language questions? I mean, I have a speculation about that, but that aside, so we found that in general, there's some what appears to be fundamental limits to at least multiplication, or some dynamic programming algorithm like problems that we experimented with. I can give you a little bit more insight about what sort of errors these models, transformers make, by the way. So we can consider multiplication through a computation graph. So when you do even as simple as 2 by 1 digit multiplication, what you do is, you do multiplication of two numbers and then store it somewhere, and then you have to add, make sure that you carry a digit correctly if you need to carry anything, and then finally arrive at this. And the benefit of drawing this computation graph is that we can actually trace back what exactly was training in the training data versus in the test data. So unlike language problems in which I may or may not have, depending on which language model you want to dissect, I may not have direct access to their training data. One can only speculate. In this case, we can actually have full access to the training data, at least if we are training from scratch. So that helps. And we found that in general, the computation graph have different width and depth, of course, and the performance is exactly proportional to the complexity of that graph. So if you multiply 1,000 with 2,000, for example, that's easy because you're not actually doing multi-step reasoning. You're just doing copy and paste of numbers based on memorized shortcut patterns. So we found that it's almost like when multiplication happens, the transformers may not be doing the true entire multi-step reasoning, but rather recognition of the subgraph that was repeated so many times in the training data, and then be able to invoke that for the final answer. So we have lots of graph demonstrating how many times certain subgraph happens has to do with that portion of computation being actually correct. I mean, maybe humans also do some of the multiplication actually this way, so who knows? I think I'm gonna skip this error type because there's more details than you want to see. I just mentioned that in the paper, we also have this appendix where we try to sketch out a theory or proof that maybe by design, there's gonna be a rapid decay with increased compositional depth. And in fact, some such, I mean, many previous papers sort of demonstrated that in different ways, but by and large, their prior work was based on weaker language models as GPT-2. So then, you know, people wonder whether there's something so magically different about the larger scale models like GPT-4, such that some capabilities really truly emerge, and you know, none of these may or may not be relevant anymore. So at least empirically, we wanted to see whether we can push the boundary further. Although, you know, we couldn't afford more GPU compute, so who knows what happens if somebody is willing to push this further up. So, but anyway, yeah.
What happens if you if instead you ask the question, give me an approximate answer to this times this, you know, 4-digit times 4-digit or 5-digit?
Yeah. Which is the new math now.
Yeah.
So it's already doing approximation on the earlier digit and the last digit better, because usually those are the places where you, and also it knows like how many digits you actually need for the correct answer. So that much of approximation seems to work, but we didn't do comprehensive analysis.
So, for example, when you gave the wrong answer, could, you know, was it really just saying, okay, let's take the least significant digit, make it 0, and then approximate and see what answer comes?
Yeah.
Is that?
It would probably do better. Yeah.
It would.
Yeah. I imagine that it will do better, and of course, you know, you give calculator, it's going to do way better. We all know that, and maybe that's exactly the point, though. And then the curious question is it multiplication just like one weird case, or are there any other aspects of language understanding or even common sense? And I come back to this common sense problem later. I'm gonna make a weird analogy to common sense later, but for now, you know, it's a little bit maybe, you know, you might wonder, are these just weird edge cases, and it doesn't really matter for other kinds of language-based problems or not? So I just wanted to throw that question. I don't know the answer for sure, but it is curious why multiplication is harder, and are there other compositional tasks? So it turns out, so my colleague Ashish at AI2, and also Will Morrell, he's a PhD student at New York University, have been thinking about this from a theoretical perspective that assumes that, you know, maybe transformers has at most log n precision. So by the way, if your transformers are infinitely precise, then it's a Turing complete. But, you know, in reality, it's not infinitely precise. It has either finite precision or maybe variable length precision, but in any case, they assume for the purpose of theorem proving that it's at most log n, where n is the length of the context. And so assuming that, you know, the weights are perfect, etc., they then look at different complexity class and conclude that if you do without chain of thought reasoning, so it's either encoder only or decoder only, but without allowing that to do chain of thought reasoning, then it may be like inside this TC0 class that doesn't include many seemingly simple enough polytime problems as graph connectivity, linear inequality. But in their follow-up work that might be still, they might come out soon, but they also consider chain of thought reasoning, and not surprisingly, it does enhance the capability a lot, so that to the point of maybe a lot of these are more possible with the chain of thought reasoning, whereas planning, as Intat mentioned earlier, also is outside what may be feasible. So this is sort of like upper bound results, as I understand, and maybe there's more to think about. But based on their speculation, it's not very clear whether multiplication should have been possible, but we just couldn't train it well enough, or there's some other tighter theoretical bound around that as well. So again, I'm just asking more questions than being able to provide answers. But that was a little bit negative, perhaps. So let's talk about something more positive.
Wait,
Yes.
sorry, I'm confused. I mean, multiplication is in, NC1 and even in TC0, right? So if we're specifically interested in multiplication, then it is in these very low classes.
No, she had limits on number of bits.
Yeah, but it's in, okay, so now we're gonna be plugging in the specific numbers, and we're gonna be saying that it's not enough. But I mean, the size of the models are, there are billions of neurons there, if we're talking about, a large language model.
So the N is the number of tokens, the size of the context. And for the size of the architecture, actually, I was curious about that too, because obviously in our experiment, the larger models are more capable. And it seems that at least, their theory doesn't touch on the size of the models yet.
Yeah, that's one more point. In practice, we have more than boundedly many layers.
Yeah.
We have more like log many layers for in real transformers, and the log precision seems too weak.
Yeah. So it's a very interesting. I mean, many theories sometimes I feel like some assumptions may or may not be immediately relevant for the empirical phenomena that we face, but I'm hoping that smart people figure something out here.
No, I mean, there are problems where we could explain the LLM's failure by saying it literally cannot represent this algorithm within the size of it. It's just that multiplying integers is not one of them. Right?
Yeah. Anyhow, let's talk about something more positive. So now the next step is about what may seem just impossible, but might be possible. So speaking of what may seem impossible, when Sam Altman was asked by Rajan Anandan earlier this year, how can Indian startups create foundation models for India? He said it's hopeless. And first of all, I mean, there's some truth to it, and that's how we feel in academia too, right? It's hopeless without much compute. I hope that it doesn't discourage Indian startups, and I hope it doesn't discourage academics to think about what else can we do. But in that sense, the following question will look impossible or hopeless. So let's just say hopeless distillation or impossible distillation. So here what we try to do is just like a bit of a thought experiment. So right now, as we all know, the winning recipe is extreme scale pre-training followed by RLHF at scale. So you do that, you get amazing results. But what if I ask the following question? What if I start with GPT-2, which is low quality small model, and then somehow bake high quality small model? I don't know how that's possible, but just for now, let's hypothesize that hypothetically. And then compete with GPT-3, which is orders of magnitude larger. So do you agree this looks impossible? Okay, so how is that even possible when imitating from proprietary LLMs are supposedly hopeless as well? So there's this paper from Berkeley here at Berkeley that says the forced promise of imitating proprietary LLMs, and the gist of it is that for the purpose of building general purpose models, just distilling the knowledge from larger models may not be enough. The larger models are just better, period. It might also be that there's something about particular task selection that the paper explored that is a little bit more susceptible to these sort of like small models looking just completely out of the league. But then there are other papers out there, even including, Intat's talk earlier, that shows, well, you could build a smaller model with, better data or better something, so that you at least have a task-specific model that is competitive against the larger counterpart. So that's the part that I'm going to explore in this part of the talk. In particular, we're going to try to do learning to abstract in the sentence summarization sense. So I just personally, I'm fascinated by the fact that humans are so much better at abstracting away what we learn and read, whereas GPT-4 is able to just attend to humongous number of tokens in one go. Nobody can do that in this room, I'm pretty sure. But there's something about human intelligence that genuinely is about abstracting away almost right away. So in that sense, we were excited to think about this summarization problem. In particular, the way that we're going to frame our challenge is the following. We're not going to rely on extreme scale pre-training. We're not going to rely on RLHF at scale. We're not going to rely on supervised data set for summarization either. And by the way, if you are in the NLP field, summarization requires either supervised training data at scale or RLHF. In fact, that's the PPO, the original algorithm, I believe, was tried for summarization task to begin with. So either summarization works well through RLHF at scale or supervised data set. GPT-4 is really good at summarization, and I don't know whether it's coming. I'm assuming that it's coming from some mix between these two, not only just the pre-training at scale. I don't know whether actually that's another question. Like, if you don't do any of this, but only do extreme scale pre-training, does language capabilities like summarization actually emerge? Or is it only the byproduct of these other steps? But anyhow, so for now, without any of that, how do we even go anywhere? So the key idea is that AI is as good as the data that it was trained on. In fact, that's sort of like the recipe behind the, the textbook is all you need experiments that Intat demonstrated, except we're not even going to distill from large model at all. We're not going to rely on supervised human written data. We're not going to rely on GPT-3 distillation either. We are only going to stick with the GPT-2. Yeah, did I convince you that this looks impossible enough? How many of you think this sounds impossible? Actually, I'm kind of curious. And this seems reasonably impossible. Or this seems like, no, I mean, probably I'm telling a story that is possible, right?
So you're going to use what size model now? 1 billion?
GPT-2.
So less than a billion.
Yeah. 1.5 billion, maybe.
Oh, the 1.5.
Yeah, the largest one. Yeah,
And
that's the
at no
starting.
point in the pipeline uses any GPT-3 or GPT-4.
No, but we are going to use other pipeline model, which is a smaller model. So there's other pipeline involved, you see, but just like small, yeah. So we draw from our earlier exploration, but this previous work where we started with the general language model to build the common sense model was distilling from GPT-3. So we asked the GPT-3, and that's, by the way, what Intan did as well, to generate some good textbook style common sense factoids that we organize into this knowledge graph, and then fine-tune smaller GPT-2 or BART. Then you get a smaller model that's quite competitive against the original teacher model. Actually, in our case, it was doing better than GPT-3 in the end. But I kind of didn't like the fact that we're relying on the larger model for the teacher. So we wanted to see whether we can get rid of it, at least for some task, as a starting point. So what we are going to do is we start with the GPT-2, which is so low quality. If you look at the output of it, it just looks so hopeless. I'll go back to this in a bit, but our goal is somehow squeeze out high quality task-specific data set. Then the rest will be breezy. It's going to be straightforward because we can do straightforward supervised training. So if you try to use GPT-2 to summarize, then what happens is that after trying so many, nothing is good, like 0% is good. So we ask it summarize, and it says a lot of random things. So after trying, say, hundreds of times, 0 is good, 0. This shouldn't be surprising even. Like, okay, this is guaranteed to be bad. So then what we do is we first try the lexically constrained decoding using our prior work called neurologic decoding. And so we identify some keywords and then see whether we could ensure that GPT-2 will generate some output that does include those keywords from the original input. And because GPT-2 is so bad, it's generally still pretty hopeless, but the chance increases from 0 to maybe 1% at this point. So the chance of generating correct summary is slightly better than before. Yeah.
Can you describe the neurologic decoding in just a little more detail? Like what exactly is it doing?
Yeah. So it's there are 2 previous papers, one of which was not the best paper, minor detail, done by undergrad student as the first author, by the way, at the time at least. And so it's a search algorithm that's built on beam search, but you need to be a little bit strategic about beams because you want to make sure that diverse patterns are covered. Otherwise, you are stuck with a very narrow beam. And so that's the gist of it. But in the paper, we actually support the full CNF form, the conjunctive normal form based logic constraints. So, but here, you don't need that much of logic constraints per se. So the paper, actually the method serves more use cases than what we actually do here. What we actually do here, on the other hand, is like a much faster re-implementation of the original paper for the purpose of this overgeneration and filtering that we need to do. Okay, so, and then students came up with a really interesting idea. So they had this intuition that GPT-2 will summarize better if we ask it to summarize its own output as opposed to human text. So they designed some left context in order to prompt GPT-2 to generate a bunch of sentences. And by the way, summarizing this part in a meta sense, there's actually more to this. But we did try different things, and we found that if we actually just try to generate a lot of continuation and then find some pairing between already generated text, then your chance of discovering the correct summarization pair increases almost up to 10%. So this is a bit totally unexpected finding just because we were trying to do something so hopeless. So we accidentally discovered that. But anyhow, so the overall framework goes something like this. So we start with GPT-2, and then we generate lots of candidate summaries, and then we are going to filter that, which I'm going to explain in a bit, to make this summarization data set. Once you have this summarization data set that's high quality enough and at scale, the rest is pretty straightforward because supervised learning almost always works well. So for the filter, basically, it's like a 3-layer filter that has length filter, because sometimes the summary doesn't summarize much other than removing one word. That's not good enough. We also have a diversity filter just to have more diverse language patterns. But the most important one is this entailment filter. So we have off-the-shelf NLI model, which is natural language inference, that tells you whether a sentence is entailed from another sentence or not, or contradicts, or none of the above. So a summary should be entailed from the original document. And so we use this. And this NLI filter is not perfect. So it's not perfect, but we could use it in an aggressive manner to ensure that the resulting summary is likely to be a good summary. And we also accidentally realized that actually we can generalize this to paraphrasing as well, because for paraphrasing, it's almost like you need a bidirectional entailment. And so we can generate lots of paraphrasing high quality data set this way as well. All right, so
So when you
yeah.
say the entailment, like you don't contradict or things like that, so this is done by humans or is this also done by?
Oh, that's automatic, and that's based on existing off-the-shelf NLI model that is a supervised model. So it's like supervised on tens of thousands of examples where it says entailment, not entailment, or actually more like entailment, contradiction, none of the above.
The data sets for that.
Yeah, there's a data set for that, which, yeah, I was glossing over that. So there's a famous data set called SNLI, Stanford NLI, and multimodal NLI that, of course, Chris Manning and others worked on. There's that, and then we have, my group also has some other data set called WANGMI, where we have GPT-3 to generate examples, and then have humans to validate. So that's a different story, but you can use any of the above, but we used the latter. But in that case, by the GPT-3 is not capable of generating correct NLI examples. So maybe GPT-4 can, but at the time we tried, not as much. It was too noisy to be useful without humans actually sitting down and annotating all of them. So here, we end up training T5 large size. This is even smaller than the GPT-2 XL, by the way. It's not even a billion parameter model. And in fact, we can do this for multiple iterations. There's no reason to stop even after one iteration. The student can become the teacher for the next generation student and then repeat this, just like human life. So then we named our data set as DIMSUM. It has 3.4 million samples, and then the resulting model is in this teal. Yeah.
When you do some distillation, do you still have a filter for good pairs? Is there a human looking at the output and testing?
In this particular, so in our own data set, we don't have a human in the loop. I mean, maybe we do have a human in the loop in the sense that we as a human designed this pipeline, but as far as a filter, it's all automatic.
Okay.
Yeah, we didn't do the paper-specific neo-annotation whatsoever.
So is there any filters on the right-hand side of the picture? Or is there no filters?
Oh, I see, sorry. The filter is here, but it's too small to notice, I realized, yeah. So the filter was there, but it's just, we're trying to say that we can repeat this multiple times.
Technical detail. So for a T5 large model, isn't it already initialized with summarization being trained in the pre-training process?
Yeah, so it probably was. We kind of liked the stick-to-stick aspect of it, I suppose. We could have just stick to GPT-2 as is, but it allowed us to have even smaller model is part of the reason. But if you just use a T5 off-the-shelf still, you will not necessarily get as good performance as we were able to. Actually, I think compared to GPT-3, T5, I think is worse at summarization. Please correct me if I'm wrong. Huh? Of the filter itself. The in-domain, so that varies a lot. For in-domain, within the, for its own training data style examples, the SOTA models are about could be beyond the 90%. But for out-of-domain cases, it can be quite a bit worse. So maybe, I don't know, ballpark guess 70. Sasha, do you want to add something?
Active on some of these. I don't think T5, I'm looking at it, I don't think it was pre-trained with summarization.
Yeah, I wasn't, thank you for clarifying that.
It's incredibly confusing because there's two variants of T5 that people use. One is T5, which was the pre-training mixture did include summarization, and there's T5.1.1, which is what everyone should use, which was only trained unsupervisedly. So whether the base model that you used was trained on summarization depends on whether you use T5 or T5.1.1.
Okay, that's good to know. I'll double check on that. The versioning is kind of crazy. Yeah, thank you. Anywho, so this is a little bit reminiscent of reinforcement learning, actually. The special variety of it called the self-imitation or expert iteration, depending on which RL group I talked to, they use a different terminology. But it's basically the same thing, which is a glorified renaming of supervised learning in some sense, that allows the model to explore its own summarization exploration, and then have this reward network, which in our case is the filter, that tells you whether it's a good summary or not. And then you do supervised training on your good experiences. So in that sense, it's imitation, self-imitation learning. So here's some example. So we're going to summarize this text, which says, while we will be looking across all parts of the newsroom, at the end of the redundancy program, we expect that there will be significantly fewer editorial management, video presentation, and section writer roles. The publisher is quoted as saying in an internal note. So our model summarized that as, we're looking to reduce the number of staff in the newsroom, the publisher said in an internal note, whereas GPT-3, first of all, doesn't look like much of a summarization compared to the original length. This is typical that GPT-3 sometimes it doesn't summarize much. And then it added a bit of information that may or may not be correct entirely, depending on how you scrutinize the original text. I should note GPT-4 is really good. I don't think this method can beat GPT-4, which, by the way, we don't know exactly what happened with their training, so we don't even know how to compare. But anyhow, one practical question though is that I said we did summarize a synthetic text as opposed to human text, and so we found that it actually generalized well on the data set that is actually written by humans for the purpose of downstream evaluation. In fact, it does do better than the model trained on human supervision data on other domains. So more experiments in the paper, and truly more diverse. It's in part because we enforce diversity in our filtering just to ensure that we have a lot of more abstractive summarization than extractive summarization. Okay, so the last bit is going to be about some paradoxes. I promised earlier that we're going to come back to some common sense related stuff. So GPT-4 passed the bar exam, and then Yosha Benjo says we have existential risk, and Yanrukun says AI is not as smart as a dog, so it's almost like everything everywhere all at once a situation. So in that context, I'm going to just throw in that maybe we have a common sense paradox. I make an analogy to dark matter in the sense that maybe there's a lot more dark matter than we anticipate. And so, some people are excited about the capabilities of GPT-4 and report that, theory of mind may have spontaneously emerged. And then, for anything like this, there's always like a counter argument that no, it's maybe it's not as robust as one may have expected. So, by the way, for this paper, the 28 seemingly complex examples may have been very similar to what the pre-training data included, whereas Tomer, Ullman at Harvard, he disturbed the examples a little bit and realized that the models are not as robust. So I have my own version of it. So GPT-3, as of last year, was not able to do the classical theory of mind. So Alice and Bob saw apples on the table in the kitchen. Alice left the kitchen. Bob, in the meanwhile, moved the apples to the cabinet. So there are two locations, two people. This is very classic. And you ask this question, and GPT-3 used to say in the cabinet, which is the later location, and it's the wrong answer. So, but that's also last year. So this year, GPT-4 is able to answer it correctly. So, the first location is the correct answer, but it may have relied a little bit overly on the fact that usually this is a bit of a trick question where the correct answer tends to be the first location. So out of curiosity, I will switch the order of the last two sentences in the story. And then, I tried the different versions, and GPT-4 kind of sticks to the first one. But, if you try to add a little bit more hint to it, the language just try to hint like, while, Alice didn't look, may be able to answer it correctly. So some people say that, yeah, you have to ask these questions more politely to GPT-4. But in any case, the thing is, humans, even if you ask not politely enough, are usually able to do this job better than GPT-4 does. And for this particular paper with Alain Sir joining Berkeley soon, we designed all these different variants where maybe there are more, like 3 people, 3 containers, or how about 4 containers? And these were designed before ChatGPT or GPT-4 time. So the paper was written originally for GPT-3. Later, we added just this GPT-4 performance, and sometimes, it's really good. Sometimes it's a little bit more varied. And then there's this TED Talk in which I did this example of drawing closing, Okay, this is like a physics. Earlier we had discussion about, how much physical knowledge does this know. So let's ask. So I asked this question April this year. I left 5 clothes to dry out in the sun. It took them 5 hours to dry completely. How long would it take to dry 30 clothes? And GPT-4 back then said 30 hours. But of course, these public examples are gone very fast. So as of June 18, this is for my CVPR keynote, I asked a different question because the previous question is solved. So it's almost same question, but slightly phrased differently, like how long, so if it takes 10 hours to dry 5 clothes, how long would it take 20 clothes to dry? If you try my original version with different numbers, then GPT-4 gets it correct. If I ask it this way, at the time of June 18th, it was incorrect. So at that keynote, I said, this kind of looks like RLHF whack-a-mole game situation. But of course, this question is also gone. So if you try this today, you're going to get the correct answer. So yesterday, I knew that, by the way. I knew that, and I didn't try any other question until last night. I thought I'm going to try a different one. How about this one? Suppose it takes 3 hours to dry a shirt and 5 hours to dry a pair of pants in the sun. So I added an irrelevant, object into the phrase, and it says, there you go, 6 hours again. So what I'm trying to tell you is this. By the way, and then I saw a few days ago, Jeremy Howard says, you have to ask the custom. You have to start with this custom prompt. Otherwise, you don't. So in which you should, prime the model that you are, autoregressive language model, fine-tuned whatever, but brilliant at reasoning and, just motivated a little bit more. So I tried, and indeed the behavior changes, but the final answer is still wrong. If you try a few, not even a few weeks down, probably will get fixed again. But
that only takes you so far.
But the thing is this, you didn't need to do any RLHF on yourself on this. Like you just know the answer. You've never seen these examples before. You just know the answer. So how does this work is my question. Like, I'm just so curious. How did we do that? Transformers, that amazing GPT-4 that can even pass the bar exam that I cannot, not able to do. So there's something really mysterious about the whole thing. So, okay, finally, the paradox is that it may be that all of these are simultaneously true in some version. So common sense is trivial for humans, hard for machines. But at the same time, Voltaire said that common sense is not so common even among humans. And then LLMs do acquire vast amount of common sense knowledge. There's nothing quite like GPT-4 that can provide as much of a common sense prior knowledge. Yet, maybe Yamnook-kun does have a point in some ways. So, Moravec's paradox, I think that this came up earlier. Maybe Alyosha mentioned this earlier, that is basically contrary to traditional assumptions. Higher level reasoning might be easier for computers than lower level perceptual stuff. So it might be to the point that maybe language is easier than vision, and we might have AGI even without embodiment that matches dog level capabilities. Who knows? So I think part of the challenge though there is that we don't have a really good data set or even pre-training objective compared to LLMs. So whenever something amazing happens, I see that there's a bit of this data innovation that comes to play, which was basically the case with the textbook is all you need, as well as the impossible distillation that we saw earlier. So there's this more actions going on about how to find the data set. Lastly, super quickly, briefly, generative AI paradoxes. So this is like made up stuff from my group that we're working on. It might be that for AI, generation is easier than understanding. Compared to how it is for humans, that DALL-E 2 is able to generate a lot of stuff, while state-of-the-art vision models are not able to see what the model is able to, AI can generate, and so forth. I actually have a little bit more concrete reasons as to why I think that way, but since now I'm running out of time, I'll just skip all of this and say thank you.
I mean, if your background assumption is that there's only one place on the clothesline for a shirt, right, then its reasoning would be completely correct. Right? In some sense, like what it's missing is this spatial knowledge of, okay, a clothesline typically has room for multiple shirts.
Yeah, I mean, depending on how you ask GPT-4, or sometimes even for the same question, GPT-4 will give you that kind of like reasoning. Oh, it really depends on how much space you have, and oftentimes when it does give you correct answer, it might be invoking that kind of reasoning. For me, it's a little bit surprising why after, and then so I thought it solved it. It's like gone, the problems are gone. And then I asked, differently phrase the question, and it's like back to the original mistake mode. And it's quite really curious. Why is this happening? Like, how does this work? Is there even a solution around this? I don't know. It feels just hard,
I mean, following Scott's question, I think a lot of times models have assumptions based on what they make a certain guess or decision making. And for human, we also have such assumptions. So far, it seems that the common ground for human and the machine are not aligned. So if there's a way, instead of just different way of prompting, if we just explicitly tell the assumptions that we have in our mind, would that solve the paradox?
You mean through prompting though?
More like, but
first explain how drawing works in physics.
Maybe I'm assuming that the machine can only take one shirt at one time, so it takes 6 hours to do 2 or something.
So I mean, so that's more like, let's try to solve this fundamental challenge through better, smart, like innovative prompt engineering. I do wonder also, can there be something entirely different? I don't know the answer, but I do wonder if there may be entirely different solution around this.
Are there any textbooks on common sense that one could use? Surely these must have been written.
Not quite, in the sense that I guess a psych is one version of trying to write down all these common sense rules that arguably didn't pan out very well, and then I also tried to build some such version of it, but through natural language description, and I tend to view that as some kind of a textbook for AI common sense learning, but it's not broad enough, it's not natural enough. I kind of feel like humans. So I like getting some inspiration from cognitive science. Humans are able to acquire more on their own. I mean, they do acquire a lot of knowledge from textbook or caregivers, but they also figure out quite a bit on their own. And I do wonder whether AI should acquire more on their own than even relying on pre-training at scale or not.
Jacob.
Could you go back to the last paradox, the generative AI one?
Oh, yeah.
Yeah, so what was this? I just wanted to see the statement of the paradox. Maybe do you have intuition for why generation is easier? Because I guess my intuition is still actually the other way around.
Yeah, I mean, so this is even within my group working on this actively, we're define understanding, we have to look at this in a different way. But in some sense, like I would say the following. Oftentimes, non-native speakers tell me that they relied on ChatGPT for some of the writing jobs. And in that sense, ChatGPT was able to generate better than they could. But then it's not quite right. And, some of the requests in the prompting were ignored. So they need to fix it a little bit to suit their needs. In that sense, like understanding was a little bit lagging behind the generation. And then for computer vision side, so by the way, for language, we tend to use one model for both purposes, which is just like transformers. Whereas computer vision is a little bit weird in the sense that their generative models are different from understanding models. And for that, I kind of feel like, generation models may be able to generate because it understood something at all, but then it's not able to communicate in language well enough so that the low-level computer vision right now, at least in my other experiments, are not reliable enough.
One could draw an analogy with cryptography and say generation is computing a one-way function, whereas understanding is inverting it. Maybe.
Thank you.
Going back to the beginning when you're talking about multiplication, it seems like when it's using the large language model, it's giving an intuitive guess. Is that kind of how you think about it?
I think it did learn something about multiplication for sure, either because the pre-training data does have a lot of examples, or because it also learns to understand even the instruction we give in the Scratchpad itself. So it does have a lot of bits and pieces understood, but being able to really accurately carrying it out is surprisingly not as reliable as one may have expected, which it does, it's on one hand, it's intellectually curious. On the other hand, it's a bit of an AI safety issue as well.
So the right way I'm going is that for the humans learn language all by their own. Whereas if you want to learn how to multiply numbers accurately, that's generally, someone figured it out a long time ago, and you're generally taught that.
Yeah.
So that's like very different kind of learning models that you would expect. But the Scratchpad helps, but doesn't necessarily get you all the way there.
Yeah, I agree.
Okay. Is there any thought to make the Scratchpad like a more firm learning model?
So a few days ago, I noticed one new archival paper that has a better Scratchpad that can boost the numbers more, but where instead of too much of natural language, maybe somehow organized it a little bit better. And that's a human intelligence understanding how to prompt this better, but still they didn't achieve amazing out-of-domain performance. It's much better than how much we were able to do. Our Scratchpad is better than the version that Google paper previously used. So we did improve over what was previously done before, but it may be that there's something fundamentally better in the prompting space. But yeah.
Okay, last two questions. So Dawn.
The early work is our early work to also show that with these neural architectures, oftentimes they don't generalize, especially for out of domain. But then when you add, for example, recursion into the neural programming synthesis architecture, then actually it could generalize. In certain cases, that can actually generalize perfectly. So I'm curious whether you guys have thought about whether you have tried to actually think about how to add incorporate recursion into either the prompt or into this space to see how this actually could help it to solve problems like multiplications and so on.
Yeah, so there may be a better way to convey recursion through Scratchpad design that might help. Somehow this was the best we had at the time of archiving. I'm assuming that you only were considering like prompt engineering as opposed to architecture being included.
Right. So maybe through prompt engineering, whether it could actually help it to learn recursion and so on. Right. So
maybe. Yeah. I feel like we don't know.
You had a slide showing this computational graph.
Yeah.
So have you tried sort of just the most naive kind of Scratchpad, which would be just literally showing this graph, one token at a time, like each node has a sequence of tokens?
Maybe not as much as that. We tried something that has less natural language and more symbolic, and that didn't pan out as well as we were. Hoping, but
the position of each token would be fixed. It would always correspond to the same node in the graph.
No, we didn't try what you're envisioning. No. I'm curious what happens if one tries.
Great. Thanks, Yejin, for a fantastic talk. So we'll break for lunch till 1:30, and you're on your own. There are lots of nice places to go to in the neighborhood. If you don't know, ask somebody.
Sure.